Pluto is a faraway and baffling planet, which was once a member of our nearby planetary family. However, recent alarming statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing an intriguing, colossal cosmic challenge, or is there more to this approaching celestial catastrophe? Join us as we explore the potential consequences of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet due to its eccentric orbit, remains a subject of fascination and study in the astronomical community. According to recent estimates by leading researchers, Pluto's orbit comes dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising alarms about a potentially catastrophic collision between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, Pluto has not yet completed one full revolution. Adding to its intrigue, Pluto's orbit is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, tilted at 17 degrees to the ecliptic plane. This steep inclination makes Pluto's path much more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune. For nearly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unusual trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricacies of celestial mechanics. The three-body problem in space involves predicting how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict their future positions based on their starting points and gravitational pulls on one another. In Pluto's case, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity interact in a complex way. Terms like mean motion resonance and orbital inclination are key to understanding this puzzle. According to astrophysicists, what keeps Pluto and Neptune from colliding is a phenomenon called mean motion resonance. Whenever Pluto crosses Neptune's orbit, it is positioned roughly 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from merging. Orbital inclination also plays a role. When Pluto comes closest to Neptune or any other giant planet, it is situated well above their orbital plane, providing an additional layer of protection from potential collisions. Another key factor in this situation is the Laplace resonance, named after three scientists who studied orbital mechanics. This resonance explains how three celestial objects like Pluto, Neptune, and the Sun gravitationally influence each other in a way that stabilizes their orbits over time. Despite Pluto's orbit appearing chaotic, this resonance helps maintain its stability over extended periods. It shows that even when celestial objects seem unpredictable, certain patterns and rules ensure some degree of order. These factors help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or veer off course. This three-body problem helps us better understand not only Pluto but also our solar system and distant universes with their stars. Numerical simulations in the late 1980s revealed that, despite its stabilizing properties, Pluto's orbit is indeed chaotic, with slight deviations in initial conditions leading to significant differences over centuries. However, these unique orbital properties have been found to maintain stability over very long timescales, effectively countering chaos. Later simulations further clarified how giant planets like Neptune, Jupiter, and Saturn influence Pluto's trajectory around the Sun. Neptune has a special relationship with Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit predictable. Jupiter's gravity also plays a critical role in stabilizing Pluto's orbit. In fact, Jupiter's gravity alone is sufficient to ensure Pluto remains on a steady path for millions, even billions, of years. Thus, Neptune, Jupiter, and Saturn work together to ensure Pluto continues to move safely through space without encountering trouble. These dynamics are crucial in the broader context of the universe, maintaining order and consistency in celestial movements. Without these stabilizing factors, our solar system would be much more chaotic and unpredictable. Bodies like Pluto could collide with others or be ejected from their stable orbits, leading to impacts on other celestial objects. For Pluto, especially with discussions about its potential collision with Neptune in the future, understanding its orbit is essential. It gives us a clearer picture of the dynamic nature of the solar system. The case of Pluto shows that even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and analysis of these phenomena to better understand our place in the universe and explore the depths of space. Frequently compels us to defy the capricious idea of divine bodies, and Pluto's circle is an ideal portrayal of this impulsive notion. The idea of orbital tumult, which alludes to the sensitive reliance of a divine body's way on its underlying circumstances, is strikingly delineated in the case of Pluto. This implies that even slight variations in the dwarf planet's position or speed can profoundly alter its long-term orbit. Using computational programmatic insights has been incredibly helpful for researchers to understand how Pluto moves in space. These simulations use advanced mathematics to show how Pluto and other space objects like Neptune pull on one another. By changing small details in the simulations, astronomers can observe how even minor changes can have a massive impact on where Pluto ends up. In the late 1980s, these simulations revealed something very interesting about Pluto's orbit. Despite having factors like angular momentum and degree libration to keep it stable, its path can still be chaotic and unpredictable. A small difference in Pluto's position or speed can, over many years, lead to a completely different orbit. However, despite this chaos, Pluto's orbit remains stable for extended periods, lasting billions of years. This means that Pluto's journey around the Sun has an order to it, even though it may seem chaotic at first. Predicting future events, particularly when they involve unstable orbits like Pluto's, presents significant challenges. The inherent uncertainty of these systems means that long-term predictions are often riddled with unpredictabilities. While mathematical simulations provide a powerful means to understand and forecast the behavior of celestial bodies, they also highlight the limitations of our predictive abilities. These models heavily rely on the precision of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to vastly different outcomes, making exact predictions a daunting task. Moreover, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we've made great strides in understanding space, the case of Pluto serves as a reminder of how our knowledge of the universe remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the position of each planet can significantly influence the stability and trajectory of other bodies within the system. So, why are prominent astrophysicists only now raising concerns about a potential collision between Pluto and Neptune? Despite all the complex forces working to prevent such an event, Neil deGrasse Tyson, a renowned astrophysicist and a key figure in promoting cosmology, offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving concept of celestial mechanics and the public's fascination with the darker realms of space. His position on Pluto's reclassification is rooted in our growing understanding of the solar system. He views the reclassification not as a demotion but rather as a meaningful shift in how we understand the diverse bodies orbiting our Sun. His approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much more there is to discover in space. The interest in these questions, particularly the potential interactions between Pluto and Neptune, highlights the dynamic and often unpredictable nature of our solar system. Tyson's work emphasizes that the more we uncover about space, the more questions arise, driving us to explore further and refine our understanding of the universe. Michio Kaku, another prominent physicist and futurist, offers a different yet complementary perspective on the mysteries of space, focusing on the often unconventional forces that shape our universe. Kaku is known for his ability to connect complex scientific ideas with forward-looking visions, making him a key voice in discussions about celestial mechanics and their broader implications for humanity. Kaku's views on Pluto and its orbit underline the need for continuous observation and advanced modeling to predict and understand potential cosmic events. He sees the interactions between celestial bodies as a crucial area of study, not only for intellectual curiosity but also for practical implications. The potential collision between Pluto and Neptune, for instance, is not just a hypothetical scenario but a reflection of the dynamic and often turbulent nature of space. Kaku's futurist outlook encourages us to consider the broader consequences of such events, from their impact on our understanding of the solar system to the possible need for future space interventions. His perspective highlights the importance of being prepared for the unexpected in space. His work suggests that the more we understand the forces at play, the better prepared we will be to navigate and possibly mitigate the effects of cosmic events. Both Tyson's and Kaku's perspectives converge on the idea that space is a realm of infinite discovery, and that our current understanding, while significant, is still limited. Their emphasis on the need for ongoing research and advanced modeling reflects the evolving nature of space science. They highlight the importance of not only understanding celestial mechanics as they are today but also anticipating how they may change in the future. The potential collision scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It underscores the need for thorough scientific inquiry, advanced technology, and a willingness to adapt our stances as new information emerges. For Tyson and Kaku, the mysteries of space, embodied by Pluto's orbit, are an exciting impetus for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a general scientific consensus that for the foreseeable future, the orbits of Pluto and Neptune will remain stable due to their mean motion resonance and the various gravitational forces acting upon them. Thus, a direct collision between Pluto and Neptune is highly unlikely. However, the complexities and potential subtleties in orbital mechanics suggest that astronomers should continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they may pose. While the likelihood of a Pluto-Neptune impact remains largely speculative and considered improbable with our current understanding, it highlights the importance of continuous study. Moreover, advancements in technology, including improved telescopes and programmatic insights, will help astronomers refine their models and predictions, ensuring we stay ahead of the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's reclassification and Kaku's emphasis on the irregular nature of celestial mechanics both stress the need for ongoing evaluation and an adaptive understanding of our universe. The potential collision scenario, while addressing the dynamic and complex interactions within our planetary system, ultimately reminds us of the vast, still unexplored areas in our understanding of space. Through continuous research and observation, we strive to unravel these mysteries, ensuring our understanding keeps pace with the ever-evolving universe.